The upcoming talk is titled VSEM for Volume Preserving Parameterizations with Applications. And the speaker is Professor Tiexiang from Southeast University. And this talk is invited talk in the section of graphics and geometric computing. And let's warmly welcome Professor Li for deliver her talk.
Okay, thank you. Hello, everyone. I'm glad to have a chance to report our recent work. Okay, so today I will report volumetric structure energy minimization model and the problem and the algorithms for the ND manifold. And this algorithm is to do the volume or mass preserving parameterizations, and we have some applications to the medical imaging process. Okay, so this is a joint work with Professor Wen Weilin in CIMIS and my PhD student Tan Zhongheng and Professor Xintong Yao. Okay, so my talk has 7 parts. So firstly, I will introduce the manifold parameterization, the concepts, and some model. Okay, so the manifold parameterization is we want to find a bijective map F. F is from the M to N. Here, the M is a manifold. Like this one, this is a 2D surface. And this one is a 2D surface, and also 3D surface, and in 3D surface, and this is a 3D manifold. So, and the N is the parameterized manifold. Usually, it is a canonical manifold, like the disk and the sphere or a ball. So, and usually, we hope this map can have some good properties, like this one. We say desired parameterization for a surface is usually based on minimization the angle distortion. Yeah, that is the conformal map. And sometimes we require this map can minimize the area distortion. So now we call the map is an area preserving map. So this is the conformal and area preserving maps for the surface. Okay, so from the mathematical way, we say for the conformal map, we say the map is conformal if the first fundamental form satisfies this equation. And here, the lambda is the conformal factor. And from the optimization model, we see the conformal map can be found by minimizing this conformal energy. Yeah, we study this problem from the energy, minimize the energy. Here, the conformal energy EC is defined this one in this way, and the first part is the Dirichlet energy, and the second part is the area of the parameterized region. Okay, so this is a continuous model, and the discrete model is this one. This is the trace of the matrix and minus this area. Okay, so we see we can find the conformal map by minimize the conformal energy, and usually we see if the energy is 0, we know the map is conformal. And for the area preserving map, we say a map is area preserving if the determinant of this matrix is a constant C. And from the optimization model way, the area preserving map between the surface from M and N, from M to N, can be obtained by minimizing the structure energy. Actually, all group developed this energy by generalize the Dirichlet energy. Actually, here we generalize this concept to the structure energy like this one, and here the LS is the Laplacian matrix respect to F. So we have a F here. Okay, so actually we have this concept in the discrete way. And of course, from the numerical obtain, we find that it's very useful, but we don't have the theory that time. But okay, so and then we generalize that idea to the volume or mass preserving. So let's see it. We say a map F is mass preserving if this equation is satisfied. And here the rho is a density function. And the density function square multiply this determinant, we require it is a constant. So if this condition is satisfied, we say the F is the volume preserving. Of course, here we have the density, so we call it mass preserving. Sorry, if the density is 1, we call it volume preserving. So we furthermore we generalize the energy concept to the volume or mass preserving. Here we see the volume and the mass preserving map between the 3D manifold M and N can be obtained by minimize the volumetric structure energy. Yeah. So VSE is these three capital. This is the name in the title of my talk. So VSE here. Okay, so we say we can get the volume or mass preserving map by minimizing this energy. Yeah, this energy is still in the discrete version. And here the LV is a Laplacian matrix respect to F and rho. So in the previous work, we developed the structure energy for the mass preserving and the area preserving based on the dirichlet energy. So how to understand this energy? Yeah, in this talk, I will give you the fundamental theory for the continuous version and the discrete version. Okay, so let's see. Yeah, based on the previous concepts, we generalize them to the ND manifold to consider the volumetric structure energy. Okay, so now let's consider all the concepts in ND manifold. Here we let M is the set of HU. U is in the Rn. So let M is a smooth N manifold with a mirror mu and the corresponding density rho mu. And the target manifold N is an N manifold topologically equivalent to M with the mirror nu and the corresponding density rho nu. Okay, so we have M and N in Rn space. So let F from M to N is homeomorphic. So for a measurable subregion A in N, so we can calculate the mass. Yeah, we have rho as a density, so we call the nu A is the mass of this subregion. So the nu A have this formula to calculate. And for the pre-region, for the pre-image, mu of this part. So this is the mass of this part. So we say, so if based on these concepts, we say the mass preserving means if the ratio of this one is equal to this one, then we call this map F is mass preserving. Yeah, the ratio is equivalent, is equally to each other, to the other. Okay, so for any measurable subregion A, yeah, we substituted that formula to here. So we have this relationship. Okay, so particularly if the density is 1, so all the concepts can be said to be the volume preserving. Okay, so we have this relationship to present the mass preserving. Okay, let's go on. Now, let's recall the ND dirichlet energy. we generalize the deletion energies concept to the ND manifold. So we define the deletion energy is like this one, Okay, so this is a continuous version. Okay, so based on, so we generalize this part. We can define the ND volumetric structure energy like in this way. So we say given two topologically equivalent N manifold M and N, we define the ND structure energy functional is this one, and here we see the dart. This the DET. The dart is the pseudo determinant. That is the product of all non-zero eigenvalues. Because here this matrix is not square, so maybe there is zero eigenvalues in this matrix. So now we define the pseudo determinant to here to mean the product of all non-zero eigenvalues. Then we defined the structure energy like this one. Okay. So we should pay attention here. So here is a ratio of this density, and here is a square. Okay. So go on. And here we have a remark to explain the energy. So let tau be an infinitesimal volume element. And then we see the structure energy can be reformulated in this way, because here we can rewrite this pseudo determinant is in this way, and then we can write the energy in this way. So we can see that actually the volume structure energy actually can be seen the integral of the square of a mass ratio. Okay. So if we focus on the volume element tau, then we can rewrite this energy in this way. Okay. So this is our continuous version for the structure energy. Okay, let's go on. We have a main result for the continuous version. And here we see if we define a set SF is all the energy for the energies, and here we require F is an orientation preserving and bijective differentiable map with the boundary condition. Okay, we require the F satisfy this boundary condition. Okay, so we have two results here. The first result is we deduced the lower bound, the energy lower bound energy is this one. This one is the mass of n square over the mass of m. Okay, so this value is the lower bound of this set, the energy side. Okay, and the most important result is this one, and we proved that if a map F star can reach the lower bound energy, and if and only if the F star is mass preserving. It means today if F is mass preserving, it must can reach the lower bound, and if a map can reach the lower bound, we can know that it must be mass preserving. Okay, so up to now we say we have completed the continuous version for the structure energy. Okay, so I will skip the proof. Okay. So we have based on this result, so we say we can find that the mass preserving parameterization can be obtained by the NVSE minimization. So how to find the mass preserving? it seems we can solve the optimization problem. Yeah, it's by minimize the energy. Yeah. So this theory give us the theory fundamental for the optimization problem. So that is the meaning for the continuous version. Okay, so we have the continuous version. Then we will go to the discrete form. Okay, let's see. Today, if we focus on how to compute this mass preserving, yeah, of course, we have to solve a discrete model optimization problem. Okay, so firstly, we should discretize the n manifold m. Or suppose the m is composed with all the n simplicity mesh. Okay, so in the discrete way, we say the M is composed with vertices, edges, and the triangulars, and go on and up to the n simplices. Okay, so here we have the figures for the 2D and 3D example. Okay, to show the discrete mesh. Okay, so for the discrete form, we see on each n-simplex tau, the F is an affine mapping. So as a result, the map F can be represented as a matrix, this one, and the matrix here, F1 to Fn is means the n discrete vertices. Okay, so and each vertex has n coefficients. Okay, so our goal is to solve the F. And if we have all the discrete vertices, we see the bijective map F is the piecewise linear and can be defined M. How to represent the any arbitrarily point P? We say for a point P in tau, so we define the Fp is the summation of this one, and the coefficient is the ratio of the mass. Okay. So with this form, we say our goal is to compute the image positions of all vertices. So we should solve all the coordinates of the F. So let's review the 2D or 3D discrete form. So for the discrete 2D structure energy, and we have this definition, and we can deduce the grading. The grading form is this one. Yeah, we can prove it. And here, the Laplacian matrix LS is defined in this way, and here the Wij is defined by the cotangent weight. But the difference is here we have to put this factor. We have to put this factor into the denominator. Here, this sigma is the ratio of the mu tau, or the ratio of mu tau and the volume of F tau, or the mass of the F tau. Yeah, this is a ratio. This is we can see it is a mass ratio. Yeah, mass ratio. We should put the ratio to here. At the beginning, we don't know why. Actually, we don't know why we must put this factor to here. Actually, if we move this factor off, yeah, when we do the computation, the iteration will not convert. And if we put that factor to here, yeah, it will blow up. So finally, we find that if we put this factor to here, yeah, the iteration can convert. Yeah. Actually, at the beginning, we don't know why, but we do in this way. Okay, so today we can explain it. Go on So for the discrete 3D structure energy, yeah, we have this structure energy in this way, and the gradient is in this way. And the LV is a Laplacian matrix defined by this WIG. In 3D version, yeah, we still have this ratio at the denominator, and this is a mass ratio. This is a mass ratio. Okay, so for the 2D version and the 3D version, our computation is very efficient and can convert. So so now, of course, we generalize them to the ND manifold. So for the discrete ND structure energy, we generalize the concept as this one, and of course, for this energy, we can prove the gradient of it is this one. Okay, so here the Laplacian matrix LV is defined by this WIG. This WIG is in this formula. Yeah, it is for the ND manifold. And here we still put this mass ratio at the denominator here. Okay, so we say we have this discrete form by generalize the 2D and the 3D version. But how to explain the theory of this one? So next, let's see the discrete version and the continuous version. Yeah, let's see, can they be matched together? Okay, so we have several lemmas. So first one, let's see the discrete dirichlet energy. Yeah, like the structure energy, we can define the ND dirichlet energy in this way. Yeah, this is a continuous version, and then we its discrete version can be formulated in this way. Yeah, and here the Laplacian matrix LD is defined by the WIG tilt, and here the WIG tilt, yeah, is in this way. Yeah, for the dirichlet energy, there is no factor here. There is no factor here for dirichlet energy. Oh yeah, like the conformal map at the beginning. Okay, so go on. Let's see. So the volume, we can use the dirichlet energy to calculate something. We say the volume of the Fm and its gradient with respect to F can be represented in this way. Yeah, we have this. Yeah, we have this theory reduced, and here we say the volume of Fm actually is equal to the trace, yeah, 1 over n trace this one, and here is the dirichlet energy form. But the difference is we have F here, so this term is high nonlinear about F. Okay, and the gradient of Fm is this one. So and here the LDF, yeah, is defined by the WIG tilt. Yeah, WIG tilt. Yeah, let's compare with the compare this WIG tilt to the WIG in the structure energy. We can find that the difference is the mass ratio here. Okay, so we can see that. We can summarize a little. So we see for the dirichlet energy, the factor WIG tilt, yeah, there is no mass ratio here. And in the structure energy, we have a ratio here. Okay, so this is the difference. And we can see they have the strong connection, yeah, in the WIG. Okay. Oh yeah, based on these formulas, we can rewrite the discrete version structure energy in this way. Okay, so finally we can rewrite our structure energy as this one. Here the tau is n complex of the m. Okay, so this actually we see the energy is the summation of this ratio. Yeah, this is this is the mass of tau square over f tau. Here is the mass of f tau, and here we have square, and here is the mass of tau. So let's recall the continuous version. Yeah, in the continuous version, actually the energy is this one. The tau is a volume element, and actually we can see in the continuous version the structure energy is here. We have the summation. Yeah, it seems they have the similar form. Okay, I can hear. Okay, there is one mu disappear, so they are likely with each other. So up to now, we say we have proved the continuous version and the discrete version is coincide together. Okay, so we say from this way, we explain why we define the discrete structure energy in this way. And these two concepts can match together. Okay. So for the lower bound, we have the similar result. Okay. So for the discrete version, we consider the set of SF of the energy, and here we require F is orientation preserving and piecewise with this condition. And here, because we consider everything in the discrete form, so the target domain is here we said the target domain is a ball, is a ND ball, and of course in the discrete situation, the volume of this ball is not a constant. There is a error, right? There is error between the discrete region and the continuous region. Okay, so here we require we will give a positive constant c and require the mass of the target domain is c. Okay, and of course this is the boundary condition. So now let's consider this set. So we can prove that this value is the lower bound of this energy. And if F star can reach the lower bound, if and only if F is mass preserving. Okay, so this theorem tells us actually we can try our best to find the mass preserving map by minimize this energy. Okay, so up to now, we have developed the complete theory from the structure energy way by the continuous version and the discrete version. Okay, so next we will propose an algorithm to solve them. So we call the algorithm is VSEM algorithm. Okay. Before we do the numerical computation, we will give a result. Is we say for the energy, because this energy is nonlinear and high nonlinear actually. So if we want to solve the optimization problem, maybe we will use the Newton or Newton-like problem the algorithm. So when we use the Newton method, so we need to solve the gradient. So here, this theorem tells us the gradient of this energy is 2 multiply the Laplacian matrix multiply F. Actually, this result is not trivial. After this proof, we can find the beautiful result. This result can help us to develop the efficient algorithm. Okay, so when we consider this equation, the gradient is equal to 0, and we divide all the vertices into two sets, P and Q, and then we can partition the Laplacian matrix LV into 4 parts. Okay, so if we have obtain some result. For example, if we have FP, then we can use this equation to solve the FQ. FQ. Okay, so it means we can construct a fixed point iteration scheme, right? It's easy to get this iteration scheme. Okay, so when we realize this scheme, we call the iteration is north-south alternating iteration. Why we call this one? That is because when we construct this algorithm, when we develop this algorithm, we want to solve the parameterization for the stereo. Okay, so for stereo. So in the 3D case, so when we fix the north part, we think the north part is known. Then we use this known part to solve the unknown south part. Okay, iteration. So now we use the south part to solve the north part. So north and the south iteration. So we call this iteration is a north-south alternating iteration, and we call it a SEM. Okay. The SEM, the algorithm is very fast, but it's not accurate enough. So go on. So we say today we want to use the structure energy minimization to solve the ball parameterization. So I'll go. So we should solve this optimization problem. Okay, this is our optimization model with this constraint. And here, the first constraint is we require the target mass is a constant C, and we require the boundary should match. Okay, but this problem actually is highly nonlinear and large scale. Usually, it's the vertex will more than 10,000. Yeah, so it's hard to solve directly. So in order to solve this problem, we separate this optimization problem into two sub-problems. The first sub-problem is for the boundary. Yeah, for the boundary means we want to find the spherical mass preserving map G. The G is map the boundary of M to the boundary of this ball by solving this optimization problem. And here we minimize the structure energy, and we require the boundary mass or area or mass. Okay, we require the mass of the boundary is constant, and the boundary should be on this ball. Okay, so it is an optimization problem with these constraints. Okay, then another sub problem is the interior sub problem. It means if we have solved the boundary, we can fix these boundary points to solve the interior points. Okay, so the next one is interior sub problem. When we fix the boundary map, and then we want to find the mass preserving map F, such that this we can minimize this structure energy. Yeah, when we solve this problem, we can use the fixed point iteration. Like the former slide. Okay, and here we have to say for the spherical parameterization, for this optimization problem, we can consider its KKT equation, and then we can solve it by the trust region method. So so actually we use the south and the north iteration scheme to several. We use them to get initial result. Okay, so and then based on that initial result, then we use the trust region method to get a more accurate result. Okay, so we see the trust region method is accuracy, but it's a slightly time consuming. Yeah, it's not so efficient, but it can get a more accurate result. Okay. Okay, so let's see the numerical experiments. So first one is ellipsoid cases. Yeah, we know today if we have a ellipsoid, or yeah, we can we can get the exact result. So now we will use this case to test our algorithm. So we have the 3D and the 4D example, and for the boundary, we compare our NVSEM with trust region method, and compare with the north and the south iteration scheme. So we can find that the north and the south iteration very fast, but it's not accuracy. Yeah, not accuracy enough. Okay, so our methods can get a very accurate result. Okay, this is for the boundary part, and for the interior part, yeah, the result is likely. Okay, so yeah, we tried many cases, and for the 3D or 4D cases, and we have this result. Yeah, usually we can see that uh, our method can get a more accurate result, and SEM is very fast. Okay, and let's see the histograms of local volume ratios. Yeah, and we hope that today the map is mass preserving. Mass preserving means the ratio of the mass should be close to 1. Okay, so for so many n complexes, so we can see mostly the ratio is combined. Yeah, is clustered at 1. So of course, for the 4D cases, the result is not so good with the 3D. Yeah. Okay, so now we want to combine the mass preserving idea to the optimization uh, uh, optimal transportation idea together. We call it optimal mass transport. Yeah, I want to introduce this idea here. Firstly, let's recall the Monge problem. We say today if x and y are two spaces with measures mu and nu, and they have the same total mass. Now, if we define a constant function kappa, our goal is to find a measurable map T. T is from x to y, such that the T star can get the minimal constant. Okay, so the T star can minimize the cost. Now we call the T is the optimal mass transport. Okay, because here here's mass, because here we require the map should satisfy the mass preserving condition. Okay, for each subregion, the mass is equal to each other. Okay, so we call this problem is optimal mass transport. Now let's because today we have the density function. Okay, so we can define the local area measure with in this way, and that is for in 2D manifold, and for the 3D manifold we can define the local volume measure in this way. So it means today if we have defined the density function, we can use the density function to define the local mass. Okay, so we have the mass on the manifold. Go on. So use all these concepts. We define what is the area measure preserving Monge problem. We call it the AOMT. Okay, so we say given a discrete simple together, close the surface M, and let M be the local area measure, and we say this is a set. G is a set for this map, and this map satisfying the G can map M to a spheric and satisfy this mass preserving condition. Okay, and in this set, we hope to find a map that can minimize the cost function. Okay, the cost is defined by the Wasserstein distance. Okay, so we call this problem is AOMT. Okay, so this is for the surface case, and for the volume measure preserving module problem, yeah, we have the different mass preserving condition here, and the F should map M to a ball, 3D ball. Okay, and we hope to find an F to minimize this cost. And here is still is the Wasserstein distance. Okay. Yeah. We combine the mass preserving and optimal transformation problem together. And now we want to use them to do some real applications. Here, I will introduce our recent work in the brain tumor segmentation here. In the past 4 years, we continuously to attend the practice challenge. Okay, so this challenge is for the brain tumor segmentation. Yeah, in this challenge, we have more than 1,000 brain images by MRI, and each brain image has 4 modalities: FLAIR, T1, T1CE, and T2, with the gray scales. And the scalar is this one. Okay, so yeah, like this image, but it is a 3D MRI image. Okay, so our goal is to do the segmentation to find the three different regions. Okay, we call it WT, TC, or ET. WT is a whole tumor, TC is a tumor core, and ET is enhanced tumor. Okay, so that is this application problem. Of course, today we want to use the AI model to do this target. Okay, but before our contribution actually is the data pre-processing. Here, I want to introduce our main technique here. For the 3D irregular brain, and suppose there is a tumor inside. Okay, suppose we know the maybe not exactly, but roughly we know where is the tumor. Then we can give the density function. We can define the density function on this image. Yeah, usually we will give a high value on the tumor region, and other position we set the row is 1. For example, we set the row in the tumor region is 1.7. Okay, so then we do our mass preserving optimization. Our optimal mass transport to firstly, actually, we transform this irregular 3D manifold to a ball, to a 3D ball, and then we do OMT map again to the cube. Okay, so here we say we use 2 steps OMT map to convert the 3D brain to a tuber. Okay, so for us, all the brain images can be transported to cubers. Then we put all this data into the AI model. Yeah, here I write the 3D UNet, but you can use any AI models. Okay, so then we do the segmentation. We predict the tumor position. Okay, so now we have get the tumor position. Then we use the inverse OMT transport. We can find the tumor region on the original brain. It can be for the doctor to check the result. Okay, so this is our main technique. Okay. So why we do the OMT to here? Okay, the advantage is in this process we say let's see the first OMT map. We map this 3D irregular brain to a ball. Okay, and because we define the different value as the density function density at a different position, we let the tumor region the density on the tumor region is higher. So because our map is a mass preserving map, so in this domain, the tumor region will be enlarged because we require the mass preserving. And here, this ball is homogeneous. So here, the mass is the brain, the tumor region is heavy. So here, the volume should be large. Then we can get the mass preserving. Okay, so let's summarize the advantage. We say the density function for the OMT can be freely controlled by designing variety of density functions. We can get different transformed cubes, which can achieve the image augmentation. Yeah, we give the difference of density function, we can get a different ball. Then we can get different cubes. So we can get more data for the AI model. Okay, and in this process, we say we enhance the density of the specific region is effectively in expanding its percent in the image. Yeah, percent image. Usually we see the volume of the tumor in the original image is about 8%, but in this image, the volume can reach 14%. Okay, so we think the tumor in this image is enlarged, so the AI model can easily to find them. So we use this idea to this challenging problem. So we transform the full modality and the labels, all the brain into the 3D cubes, and then we use AI to do the segmentation. And our result is very beautiful. Yeah. Actually, in the 2023, we for the three different region, this is our result. So for the TC and the ET, our result is the number one, and for the WT, we are not number one. Yeah, the first number one is NVIDIA company. Yeah, you know, NVIDIA company has a lot power, GPU power. Okay, so but we just have two GPU cards. Okay, and we have with more different data from the medical school. Then we published the paper in PNAS. Okay, last week. Okay. Okay, so I will give a conclusion. So in this talk, we propose a continuous ND volumetric structure energy function on M, and this structure energy have the lower bound, and we proved that the minimizer of this volume of mass preserving if and only if the minimal energy can attain the lower bound. Okay, and we proposed a discrete form, and which corresponds to the continuous version. And for the discrete structure energy, and its gradient can be simply expressed by the Laplacian matrix, and we developed the efficient algorithm. And we propose the OMT algorithms for the spherical and the ball mass preserving parameterization and apply them to the brain tumor segmentation. And the segmentation accuracy is very good. Okay, so I will stop here. Thank you.
Thank you for Professor Li's valuable and interesting work. And now we have some time for questions.
One to one? No. Yeah. In continuous version, of course, we require is a one-to-one. But in discrete version, when we do the real computation, maybe the folding will happen here. Here, when we do the numerical cases, we can find that, for example, in this case, we have three n simplexes folding, and we use a post process to trade off. So here, this is the folding removal post process, and we use it one time, so all the folding disappear. Yeah, and sometimes if the domain is is not smooth enoughly, and here maybe even we use the folding removal, still there is some folding here. Sometimes it's hard to avoid. But we think we have explained this situation in our paper. Uh, Actually, when we use this algorithm to do some parameterization, actually it can be accepted. Yeah. Uh, Domain, the M. If the domain is good enough, so there is no folding, you can stay here. Some just for the very bad case, the folding maybe, yeah. Yeah, this one there is no folding. Yeah, this one is a very not convex. Yeah, if we think if the domain is convex, the result will be very good as a no folding. But for this case, it's very bad, so there is more folding here. And we have to use several time folding removal post process to remove them. Yeah. Um, very. No. Uh, Sorry. So I don't know. You can use yeah, Chinese. Uh, Not sure. Yes. We discovered the folding. It's not always on the surface. Not always on the surface. Sometimes interior. We don't know why. What? A folding. Uh, in the 2D, it's a triangular. In 3D, it's as a continuous way, all the theory can guarantee is 1-to-1. No, but actually, I have to say, actually, the mass preserving map cannot be guaranteed existence. Existence is not guaranteed. Maybe there is no mass preserving map. Yeah, yeah. Oh, we think in the discrete version, usually if the M is smooth enough or convex, there is no folding. Sometimes there is a little, not yeah, maybe usually there is several folding. We tried many cases for more than 400 cases, and when we use one time for the FR, just folding removal, you use one time. So most of the cases there is no folding exist. Use one time. I think that is because we are doing the numerical computation in the discrete way. So maybe the mesh is not good enough. You know, so maybe at the beginning the mesh if the mesh is very bad, so the effective cannot be guaranteed. Indeed. Yeah, yeah, it's a fact.
To pure UNet method, what's the benefits of when you're using OMP?
Yeah,
we can directly plug the image into the UNet, right? Why we use OMP?
Why I use UMT
Yeah.
here?
Yeah.
You know, so at the beginning for in this application cases, I will explain it. Okay. So we are get the MRI image. It's a 3D case. So the brain actually is put in a black box. You know, actually for us, we want to find the tumor position. So the black position is useless. So and now today our computer is not yeah, we have not so enough computer storage. Okay, so we want to avoid this. We want to trade off all this black
So you want
position
to
of
delete the background, right?
yeah we want to remove the background.
Okay.
Yeah.
Okay. Yeah,
So so we transform the brain to a ball, then to a cube. So the brain, the background is disappear. So
okay.
low storage.
Yeah. Why you assign density to the tumor? Right. To me,
Why?
Why you tell me to assign some density to the tumor? You assign 1.7, 1.8.
Yeah.
To me, it seems that the larger you assign the value it is, the better the result may be.
Yeah.
Is that story?
You mean the density is large?
I can set the density to be maybe 10.
No. Too large density. Yeah, you know, other information will disappear. So maybe because when you set the density function or density value, actually you don't know where is the exact tumor. So actually you just know the roughly where is the tumor, roughly, not exactly. So you need other information actually. So if you set the density is 10, the tumor will be enlarged too much. You know, other maybe useful information will disappear.
So there is a trade-off.
The larger density will not guarantee the better.
Parameter, right?
Yeah.
You need to tune it to get the best performance. Right?
Yeah, usually we set 2 or 1.7. Yeah.
Okay. Yeah.
nearby 1.7.
Any other question?
A simple question, and you use the two-step. Is
Two-step OMT.
you have to use. Is it possible to make it one step? And I think that if you make it two-step, then I mean it's.
用中文好吧？
我认为呢，它如果是两阶段的，那么就应该算是一种贪婪算法。
贪婪算法。
因为你没有直接去优化这个 F。
我这里就是我这个因为没有讲很清楚，我这个两阶段啊，就是我这里的两阶段是想说，我是怎么从几何计算的角度，我怎么从这个脑到这个方的，它不是一下子过来的，它是先从这个脑到这个球，然后再从这个球到立方体的，是就这条线它是经过两步，这个两次。但是我们其实整个的这个模型，我们这个 segmentation 的这个过程实际上是两次。就刚才说，你怎么去设这个密度density 方式，你怎么去 set the density？ 一开始我并不知道肿瘤在哪里，所以我们先做了一次。
一开始是一个 boundary 的一个 step， 然后一个是 interior。
一开始我们并没有用 OMT， 一开始就是用传统的一般的这种方法，就是把它切成几小块直接丢进去的，没有用几何。大概预测出来肿瘤在哪里，然后再给它赋密度的。好，我用英文讲不清楚噻，所以我有两阶段的概念。一个两阶段是我的脑是怎么到立方体的，我的脑先到了球，然后又从了球到立方体，这是 OMT 的阶段。另外一个是我整个 AI 的过程，我们先预测了一次肿瘤大概在哪里，然后在这上面赋密度，然后再来做这个 OMT。两阶段。
那么有没有可能在第二个阶段反过来再去改进第一个阶段的结果？因为这两个阶段肯定是相关的。
是这样子。如果我们花很多的力气去改呀，就是我们因为今天这个事情，我们除了讲究这个精度以外，我们还要讲究时间。就我们没有在这个事情上花太多的力气，因为我们这个跟医院合作，医生说我们的结果已经非常好了，所以我们就在努力做后面。所以这个整个事情是不是还可以再 update？ 当然可以继续，是的。但这个就会花更多的时间。我们希望在几分钟里面就对这个肿瘤的结果有一个判断。但我们现在最新的这个工作，除了找到肿瘤在哪里，还对这个肿瘤的恶性程度、肿瘤的基因类型都做了分析。也就是说，是一种非侵入式的肿瘤的分析结果。那我们想要追求一下效率。
Thank you。
谢谢。
Any other questions? So if there is no more question, let's conclude this talk. And thanks Professor Lee again, and thank all of you for attending.
好，谢谢。好。